So we've been talking about different types of reuse, which includes self-temporal reuse, self-spatial reuse, and group reuse. And the question is, which is more important? I mean, as a compiler developer, which one should I focus on more? Which one has more payoff? And which one has less complexity? And so we're going to answer that question a little bit qualitatively in this particular module. Significance of reuse. And in general, the more reuse there is, the more potential for caching there is. Notice that we have been talking about how reuse is different from locality. Locality involves reuse and small reuse distance, whereas reuse can have a large reuse distance. And so locality is meaningful for certain types of caches, such as caches that obey the principle of temporal and spatial locality. On the other hand, reuse can be used for different types of caches. For example, you can influence, depending on what kind of reuse distance you see between different accesses, you can influence the cache replacement algorithm. For example, there are different cache replacement algorithms like least recently used, first in, first out, least frequently used, or other such algorithms that you may have been introduced to. And some of these algorithms are more meaningful for locality, workloads that exhibit locality. For example, least recently used basically gives more importance to recency. And so that makes more sense if there was locality in the workload. Whereas least frequently used does not really care so much about recency, it only cares about frequency. And so depending on what the compiler inferred about the program, based on this analysis that we are doing, the reuse analysis and the reuse distance, it can influence the caching policy. Now, how can it influence the caching policy? First of all, caching is happening at multiple levels of the computer system stack. It is happening first at the compiler level itself, because the compiler decides what to keep in registers, what to keep in memory. There are some machines where the caches are software managed. These are also called scratchpad memories, in which case it's up to the compiler or the software to basically say what lives in the scratchpad and what lives in the main memory, which is more expensive or which has higher latency. And so in all these cases, such analyses of the program and the reuse can help influence what policy the software should use to keep what stuff in the scratchpad. In general, hardware caches are the most common types of caching available, and hardware caches typically prefer recency over frequency, because locality is by far the biggest, most common pattern that gets exploited by caching, and that gives the best payoff across a large variety of applications. And so if it's possible that you already have low reuse distance, in which case you have locality, and the hardware caches are going to help you for that. There are some research proposals for hardware where they allow the software to basically change the caching policy of the cache. Maybe there are 2 or 3 different caching policies that the hardware supports, and you can switch between them. And depending on what you have inferred about the amount of reuse and the reuse distance, you can switch between different policies. So these are all the different ways in which this analysis of reuse can help us in improving the performance of a program. So the 3 main categories that we have learned so far, and if I was to compare the 3 categories in terms of their importance, then self-temporal reuse is the most consequential, because it gives me the maximum amount of reuse typically. For example, if there is a k-dimensional null space in my capital F coefficient matrix, then that immediately gives me order n to the power k reuse. So recall that if the matrix, the coefficient matrix, was not a full rank matrix, then its null space would have some non-zero dimension, and so whatever is that dimension, you get that much amount of reuse, and that basically is the most consequential. Once again, if there are order n to the power k reuse, there are many ways you can exploit that. Number one, you can make compiler transformation so that the reuse becomes close together in time. In other words, the reuse distance reduces, or you can influence the caching policies for scratchpad or the hardware caches and stuff. Then self-spatial reuse is also important, but it is less usually limited by the cache line size. Recall that we are making a very major assumption when we are kind of doing analyses for self-spatial reuse, assuming that the entire last dimension is basically available in the cache we just make that assumption, but in reality we are limited by cache line size, and so in reality the efficacy or the improvements that we get due to self-spatial reuse are limited by the cache line size, and so it's not as consequential as self-temporal reuse. And finally, group reuse. Group reuse, we are primarily focusing on group temporal reuse in our module, and so it is also limited because it's limited by the number of references with the same coefficient matrix. So what is the probability, how many accesses in your loop nest have the same coefficient matrix? Only those accesses will basically be participating in group temporal reuse, at least based on our limited analysis, and so that also limits the efficacy of group reuse.